First of all, I would like to thank you all for agreeing to listen to me for 2 hours. I don't remember when was the last time anyone was agreeing to do that without asking for credit points.
So far, only for the start.
Oh, okay. Okay, so we will start with slides and then move to Blackboard. And this talk is about combinatorial PCPs with short proofs. So let's recall what PCPs are. So suppose that someone wishes to convince us that some NP claim holds. For example, that some 3CNF formula is satisfiable. Then a PCP is a proof system that allows us to check that, or that allows him to convince us that the NP claim is correct by providing us with a special proof. What's special about this proof is that in order to verify that the prover's claim is correct, we only need to read a few bits out of the proof, and still with a high probability we will be able to make the right decision. So in this setting we think of two parties, the prover who wishes to assert some claim, and the verifier who wishes to verify this claim by reading only few bits of the proof that the prover gave. Since this is a central definition, and I'll make the formal definition. So a PCP V for a language L with query complexity Q, rejection probability rho, and proof length L is a probabilistic oracle machine that takes some input W, which represents the claim that the string W belongs to the language L. And we think of V as being given oracle access or black box random access to some proof string that is provided by the verifier, by the prover. Now, the requirements are that V makes at most Q queries to its oracle, where Q could be a function of the length of the input, but will typically be small. Then we require completeness. That is, if the claim is correct, if the input W indeed belongs to L, then the prover has some way to convince the verifier that the claim is correct. That is, there exists some proof that, of length at most L that will make the verifier accept if probability 1 when V is given oracle access to the proof pi. And then we require soundness, which means that if the claim is incorrect, if the prover is trying to cheat, then no matter what the prover does, no matter what proof he's providing, the verifier, here it should, okay, forget about the X here and replace AB here with W. So no matter what the prover does, the verifier will catch the false claim with probability at least rho, where rho again could be a function of the length of the input. Questions? Okay. So the next most important thing you need to know about PCPs is the PCP theorem, which says that any NP language L has a proof system, has a PCP that has constant number of queries, constant rejection probability, and polynomial proof length. And this is quite amazing because, I mean, NP is the language, is the class of languages for which we have standard proofs of polynomial length that you need to read, where you need to read all of the proofs. So this says that we can have these amazing PCP proof systems and still have only proofs of polynomial length. And besides, it has a lot of applications. Now, since the original theorem was proved, there have been many works trying to improve its parameters, in particular the query complexity, the rejection probability, the proof length, and also the running time, which we will not discuss at all in this talk. And in this talk, we will actually focus on the proof length. And in this case, the state of the art is n times polylog n, where the query complexity remains constant and the rejection probability remains constant. This is due to a combination of works of Ben-Sasson and Sudan and Dinur. Hmm? Oh, great question. So for this talk, you can think of n as being the length of the NP witness. I mean, if the original NP proof was of length n, then the PCP proof will be of length n times polylog n. Actually, I'm little lying. Technically, the correct statement would be that if the running time of the PCP verifier is t, then the PCPs have length of t times polylog t. But for this, okay, we will ignore this technicality. Okay, so how do people prove the PCP theorem? So the original proof of the PCP theorem and many of its improvements are based on what we usually refer to as algebraic techniques. That is, given some claim to be verified, they transform the claim into some algebraic claim about low-degree polynomials using a technique called arithmetization. And then they use the properties and structure of low-degree polynomials in order to prove the claim. Then in 2005, Dinur gave an alternative proof of the PCP theorem that uses simple and intuitive combinatorial techniques. So this is the so-called combinatorial approach. However, Dinur's proof of the PCP theorem only gives PCPs of polynomial length. It doesn't give PCPs that have short proofs. So this gives rise to the natural question, can we give short PCPs that using combinatorial techniques such as Dinur's? And this is the question we will focus on in this talk. But before that, I will want to tackle an easier question, which is why care? So why would someone care if we use algebraic techniques or combinatorial techniques as long as we can construct our PCPs and they work well? So there are a few answers to that. First of all, one may say that it's always good to have more proof techniques. I mean, why not? More techniques, more ideas, this is always good. Another reason is that some researchers, and I among them, believe that the combinatorial proofs are more intuitive and give us more understanding about what's going on. And another reason that is not usually mentioned, but I believe is true, is also important for this talk, is that combinatorial proofs allow us to understand better the role of polynomials in PCP constructions. And by this I mean the following. Well, polynomials are doing a very nice job in PCP constructions. They are working very well, but it's not completely clear what role do they exactly play. What makes polynomials so special or so helpful in PCP constructions? In most constructions, we use a variety of properties of polynomials, but it's not clear what is really the essence of polynomials that we need for PCP constructions. And I think that this is also a good question. And one way to try to answer this question is just to try to remove the polynomials and see what happens. So this is another motivation for the combinatorial proofs. Okay, so this is the motivation. Now what do we actually do in this work? So we get close to achieving our goals, but we don't fully achieve them. So in particular, we can construct combinatorial PCPs that have a proof length of n times log n to the O of log n. While the state of the art is n times log n to the O of 1. This is quite close, but it's not the same. Then, in our construction, we still use polynomials, but in our case, we actually managed to isolate this use of polynomials to a particular and well-defined property of polynomials. So I would like to argue that we still make some progress here. We managed to say exactly what do we want of polynomials. And I want to get it off the table and say what this property is, and I will do it in 2 slides. But in the next slide, I first need to do a quick recalling of the basics of error correcting codes.
What do you think about combinatorial PCPs that compete in the other parameters? Like, is that be doable too? Like 3
That's a great question. That's actually my PhD thesis. I mean, yeah, we have results that compete in all of the parameters, I think, except maybe few particular ranges. Okay, so okay, so error correcting codes. So a linear error correcting code, or just a linear code, is some linear function that maps messages of length k to code words of length n. And this is an encoding that serves purposes of error correction. And we usually refer to k as the message length, because this is the length of the messages, and n, which is the length of the code words, is the block length. And again, the code words are just the images of the mapping. And the error correction property of the codes is the so-called relative distance, which is and we say that C has relative distance delta, where delta is some fraction, if every two distinct code words differ on at least delta fraction of their coordinates. So these are the basic properties of codes, and an important thing to know about them is that for any message length, we can construct codes, the linear codes that have linear block length. That is, the block length is a linear function of the message length, and also have relative distance, which is a constant that is independent of the message length.
You use the narrative.
Yes. Yeah, here, this is another use of algebra, you may say. Also, okay, so the next thing we want to say about it is that for linear codes, we can always assume they have what's called systematic codes. That is, for every message, when we encode it using the codes, the original message is included in the encoding. That is it. And in particular, say that if we project a code word to the first k coordinates, we get the original message. Okay, so now I can state the property of polynomials that we use. And the property of polynomials that we use is that polynomials are error-correcting codes that support multiplication. Or formally, we use polynomials to construct what we call multiplication codes. So we say that three linear codes, CA, CB, CM, form a multiplication codes triplet if whenever we take one code word of the first code and a second code word of the second code and multiply them coordinate-wise, we get a code word of the third code. And this is just a generalization or abstraction of the property of low-degree polynomials that says that if we take a low-degree polynomial and multiply it with another low-degree polynomial, we get a low-degree polynomial with slightly higher degree. Yes?
You don't multiply coordinates, but you want to say that the image you will multiply.
These are evaluations.
Yeah, usually the polynomial code is to take the polynomial and evaluate over many coordinates. Yeah.
The thing of multiplication over G equal to.
Yes, right. And in general, over a larger field, it will be multiplication over the field over which the codes are linear. Okay, so for polynomials, it is easy to construct multiplication codes that have a linear length and constant relative distance. Here I'm little lying. To do this, we actually need a larger alphabet, but we will ignore that in this talk. So we will assume that we have codes of linear length and have this multiplication property and are binary. And I would also like to mention that if we don't want to use polynomials, it's actually possible to construct them it's actually possible to construct such codes, but then they will have quadratic length. The block length n would be a quadratic function of the message length. Yes.
Can you also get linear length over X2 or just over the other fields?
I think I only know how to do this over larger fields, but maybe using algebraic geometry cause it's possible to do it over binary. I don't know. And also, okay, we can discuss it more offline. Yes.
You could argue maybe that for the combinatorial proof, you not mention finite fields at all. So do you think that could be?
That's a good question too. I agree. I use linear algebra in this proof, even though I try not to use. I mean, I don't use polynomials, but I do use linear algebra. I would be happy to get rid of the linear algebra too, but I don't see how to do it.
Is the best thing we can do this combinatorial, since combinatorial setting is quadratic elements and lower bound, we just don't know how to do it?
We just don't know how to do it. I mean, I think it's entirely plausible that one can do it without polynomials. And actually, we don't even need the linear length. I mean, we need in order to get our results, linear length is enough and quadratic length is not. But what we actually need is just almost linear length and say relative distance that is 1 over polylog n or something like that. That would also be enough. And I think it could be the case that it is possible to construct such codes without using polynomials. I think it's an interesting question. More questions? Okay, great. So okay. So now I will now give a high-level overview of the PCP construction, and then we'll move to the blackboard and give some details. But in order to give this overview, I first need to define an important notion called a linear PCPP. And the linear PCPP is, you can think of it as a PCP that is specialized for verifying linear claims. And a bit more specifically, it's a proof system that gets oracle access to some vector and verifies that it has some linear property by reading only a few coordinates of this vector and of an additional proof. So, and a bit more specifically, so a linear PCP is a verifier that takes as input some linear subspace of 0, 1 to the n, and gets also oracle access to some vector x and to some proof pi. And the linear PCPP should verify that the vector x belongs to the vector space W by making only few queries to x and pi. And two comments. First of all, the motivation for this notion, at least for this work, is that hopefully linear PCPPs would be easier to construct because we only focus on linear claims. And also, know that it's impossible to verify that x actually belongs to W by reading only few queries, because it could be that flipping one bit of x would make it not being in W. So the actual definition, which I'm going to give in a second, will be a relaxation that says that if x is far from being in W, only if you need to flip a lot of bits in order to make x be in W, then we will catch the error with good probability. Okay, so now let's move to the full formal definition.
Sorry, I didn't understand the justification for why you couldn't hope to do it exactly. I mean, you also have pi, right?
Right.
But,
okay, so if you can think of x as also being provided by a malicious prover. So if the prover wants to cheat us, what he will give us is he will start with some vector x in W, and will provide us with this, and will take the legal proof pi for this vector x in W. But then he will give us x prime and pi, where x prime is just x with one bit flipped. And then, I mean, we will only find the error if we if we happen to read this particular bit that the prover flipped. And our probability to make this particular query is very small. Is this okay? Okay. Okay, so let's give the formal definition. So again, we have some Oracle machine V, and it has query complexity Q, a parameter that we will call the rejection ratio, rho, and proof length L. And the verifier gets vector space as an input, say by specifying basis. And Oracle access to X, to a vector X, and to a proof pi of length L. And V makes at most Q of n queries to its Oracle. It reads at most Q bits out of X and pi. And we require two things. First, completeness. If X belongs to W, then there exists some proof that would convince the verifier to accept with probability 1. Second, if X is epsilon far from W, that is, it has Hamming distance of at least epsilon, relative Hamming distance, from any vector in W, then no matter what proof the prover gives us, the verifier will reject with probability at least rho times epsilon. Yes?
Just to understand the setting, like if the order of things, the prover is trying to prove that X is in some vector space, or the vector space is chosen a priori, and the question is whether X belongs to this vector space or not.
The vector space is chosen a priori. It is given as an input to the prover, to the verifier and the prover. You can think of the vector as chosen by the prover or as chosen a priori. It doesn't really matter. But anyway, we need to find also cheating vectors. Yes?
What do we read that a vector space that W requires some efficiency?
Yeah, say by its basis. Say the W is described by a basis. Any computationally efficient way would be fine. Actually, since you already mentioned it, in the actual proof we will want W to be specified by some circuit that computes it, and all the parameters will depend on the size of this circuit. But again, this is a technicality that we will ignore.
So the linear PCPP refers only to the linearity of W in subspace. It has nothing to do with, for example, the valid proof pi being a linear function, or the tests made by the verifier.
Actually, the tests will need to be linear, but this is another technicality I want to ignore.
Have to be linear for your application.
Hmm?
I mean, they're going to end up being linear, or they need to be linear for your application?
I need them to be linear, you know, because I will, and they can be linear. As I will say in few slides, I will want to apply composition, and then you have to use. Other questions? No, but wow, these are great questions. You're catching all the points I'm trying to avoid. Okay, so now that we have this linear PCPP, let's give the construction overview. So we work in two main stages. In the first stage, we construct a linear PCPP with the desired parameters: constant query complexity, constant rejection ratio, and the proof length that is log n to the log n times log n to the log n.
So this is like having a PCP for particular type of language, just membership in W.
Exactly. It's not okay. Actually, not, because in PCPs you get the input explicitly, and you need. This is a special case of what's called PCPP, but again, ignore it. Okay. So the next step would be to show that every linear PCPP can be lifted in some way or be used to construct a full-fledged PCP. That is, if you are given any linear PCPP, we can use it to construct a full-fledged PCP, and this will have comparable parameters. That is, even though we can only verify linear claims, we can somehow use it to verify general claims. And I should say that this is actually implied by a theorem of Ben-Sasson and Sudan from 2006. Actually, their theorem is much stronger, but our proof is much simpler and much more direct, and is also combinatorial. Okay. So before going to the details, I want to give some more high-level overview about the construction of the linear PCPP. So what we want to do is to construct linear PCPs with constant number of queries, rejection ratio constant, and proof length of n times log n to the O of log n. And I would like to argue that it suffices to construct a much weaker linear PCP. Specifically, that it suffices to construct a linear PCP that uses about square root n queries, that only has rejection ratio of 1 over polylog n, and has a proof length that is slightly better, n times polylog n.
So this will be somehow similar to the Dinur Weingold?
No. Their construction, for example, doesn't have proof length that is n times polylog n.
I know, I'm just, they do a recursion stuff.
Mhm.
Something like what complexity with that.
Yeah, actually many constructions do that. For example, the Ben-Sasson Sudan construction that achieves the best known PCPs in terms of length also do that. What I'm doing here is actually standard. We are first construction a weak PCP that has very large query complexity, and then using two known techniques called PCP composition and gap amplification technique of Dinur, we can improve the parameters to constant query complexity and to rejection ratio that is constant while paying a little in the proof length and turn it into n times log n to the O of log n.
You're losing this log n to the log n now because you're only making root n progress? I mean,
Yes. There are going to be iterations in which
you have to do log n iterations.
exactly. In each iteration, I'm taking a square root of the number of queries, and then until I get to a constant. This gives a log n iterations. But in each iteration, I also lose a factor of polylog n. So I end up with O of log n. OK, but anyway, if you don't know the composition technique and the amplification technique, you can ignore it. We are not going to discuss it in this talk because this is a standard, and we can continue our discussion without it. I would also like to make an advanced comment to those of you who know composition, and to say that the composition here is not entirely trivial, and we need to develop a new robustization technique to apply it, but I will not discuss it today. OK, so now how do we construct the weak PCPs, those that have query complexity of square root n? So our linear PCPP, when given some claim, will verify it again in two steps. So it will start by taking the claim, which is, say, of size n, and decompose it to about square root n smaller claims, each of size square root n. And then in the second step, the verifier will verify that all the smaller claims are correct simultaneously using only square root n queries. And hopefully this is easier because, I mean, now the verifier has enough queries to read some of the claims entirely and also read few bits of each of the claims. Now, in this talk, I'm not going to discuss the decomposition step because it is not very interesting. Basically, this is some kind of a sophisticated version of the reduction from circuit SAT to 3-SAT. In this reduction, what we are doing is to take a circuit, claim about the satisfiability of a circuit, and we transform it into a claim that a collection of small clauses are satisfiable simultaneously. And here we are doing something very similar. We are taking a big claim of size n, and we reduce it to a claim that a collection of square root n claims of size square root n are satisfiable simultaneously. We will need to do a slightly more complicated reduction than the circuit SAT to 3-SAT because we needed to satisfy some properties for the composition, but there is nothing very interesting here.
There's some intuitive reason why the square root n pops up as opposed to 3.
We could choose actually any parameters that where the size of the smaller claims times the number of claims would be about n. We could decompose it any way we want. It's just the best way to do it is this choice of parameters.
So,
Yes.
the description of W is usually quadratic
Yeah, so this is a technicality I wish to ignore. What we will actually want is to have some circuit that, describes
Yeah,
W.
then you have to, then when you do the decomposition, you also need to get something that with a small circuit.
Right. Yeah, all the parameters here will be actually, whenever you see n here, you can think of n being the size of the circuits. So the smaller claims are described by circuits of size square root n. Okay, so this.
Just, I understood this. So
Sure.
if I understood the question, I mean, the whole task here is to get length very close to n, where n is the size of the NP witness, original NP witness. So
Mhm.
subspace cannot be described in quadratic number, or the circuit computing membership in the subspace cannot be allowed to be quadratic in the size of the NP witness.
As I mentioned at the beginning of the talk, the rigorous statement would be that if the original NP verifier runs in time t, our proofs will be of length t times polylog t. So if we know that the original verifier runs in times t, we know that we have a circuit of size t that describes the claim, and then we will. But it's a great question, right? But okay. So now we are okay. So this finishes the overview part. So what we will see in this talk is how to lift linear PCPs to full-fledged PCPs, and how to verify square root n claims of size square root n using only about square root n queries. And okay, so this concludes the interesting part of the talk. Now we will move to the more interesting part of the talk. Okay, so let's start with where is the white? Okay. So let's start with the lifting of linear PCPPs to PCPs. Or in other words, what we want to do is we have linear PCPP V, and wish to construct PCP V prime. And the construction of V prime will use the linear PCPV as a black box. Now, the intuition for why this construction works, or how it works, is that okay, we are able to verify linear claims, and we wish to use it to verify non-linear claims. And the point is that we can use the multiplication codes that we have for moving from linear claims to non-linear claims. So specifically, as usual in such constructions, we don't need to construct PCP for arbitrary NP languages. It suffices to construct a PCP for an NP language. So we will choose, just for convenience, the language of quadratic equations. So I'll remind what this language is. Or, as always, languages describe decision problems. So the decision problem is as follows. We get a system of quadratic equations, which is of the form, say, alpha 1 I j xi times xj equals beta 1. And we have several equations like this. Now, the variables x, I take Boolean values. And the question, the thing we need to decide is, given such a system, is it satisfiable? Is there an assignment that satisfies this system? And in order to construct a PCP for this language, what we need to do is to construct a verifier V prime that takes as input such a system and gets Oracle access to some proof, and makes few queries to the proof. And if the system is satisfiable, the verifier accepts with probability 1, and if it's unsatisfiable, it rejects with good probability. Okay. So how will we do this using our linear PCPP? So the prover provides us some proof pi. And so first we will ask the prover to provide us with the satisfying assignment for the system. This is just the standard NP witness, and now what we will want to do is to check that X actually satisfies the system. But we would like to do it using the linear verifier, but the linear verifier can only verify linear claims, and this is these are quadratic claims, so we can't really do that.
So what is the size of the input? So suppose we have n variables, then you think of the size of the input.
I think of the size of the input n actually as the total number of non-zero of terms in these equations that have non-zero coefficient.
So it might as well be dense.
Yes, but then I am allowed to use more. Yes.
So but in this case, you can give also the product of x, I, and j as
Right.
enough.
Okay, so let's assume for this talk that the system is sparse, just to make things easier.
Sparse mean you have just a constant per equation.
Yeah, for example.
Yeah, then
Say every equation has only 3 terms with non-zero coefficients. Okay, so now the verifier. So the next thing we'll do is to ask the prover to give us an additional string that would help us verify it. So let's call this string y. And what the string y would contain is for every term that appears in the system with a non-zero coefficient, say xi times xj, the string y will contain the value of this term. That is, it will contain the value that that small xi times small xj. So now what we will do is just a second. So this is what we will ask the verifier the prover to give us. And the system of equations is now a linear system of equations over y. So we can use the prover to verify that y satisfies this system of equations. Yes, Ilya?
Two principles. I don't know. When you define QE, you also allow like not only pairs of variables, but also allow like single variables.
Yes, you can think of that. It doesn't really matter. You can think of it as xi squared.
by the way, you can take any this is an anti-complete language. You can start from
The second question about y, just to verify, you look at the whole thing. If you have x, y, and xj anywhere in any equation, you say you want the value of this.
Sorry?
You say about y, you look at the whole set of equations. If x, say x 3 times x5 appears anyway, even one time, then you want the value of this, right?
Yes, I want exactly. I want the value of every term. I want y to contain the value of each term in these equations. Okay, so it seems that we are.
I'm using that in order to have a combinatorial PCP, you choose an algebraic NP.
This is just for convenience of presentation. I could work with resat just as well. Yes. So it seems that we are done, right? Because we can use the linear PCPP to verify the claim now. Because
To verify that xi, xj will equal the appropriate y.
Okay, so you are following. Anyone else sees the problem? Why we cannot just conclude here because we can use the linear PCP to verify that y satisfies the system? Right. I mean, it's true that we can verify that y satisfies the system, but we don't know, but it doesn't necessarily mean that x satisfies the system. It could be that the prover provided us with some string y that has nothing to do with x. So we need to check that y is consistent with x. And in order to do this, we will ask the prover to give us two additional strings, call them u and v. And u and v are just going to be projections of x such that y equals u times v. Or in other words, for each term in the quadratic equations, say for each term xi times xj, u will contain xi and v will contain xj at the same coordinate.
That multiplication is for coordinate-wise of the vector.
There is no multiplication here, right? Here, yes. Here the multiplication is coordinate-wise for the vectors. Is the definition of u and v clear?
You want to represent
Is it okay?
I don't understand. Why are they not just do it?
No, it's just this is a little bit of repetition. So it's,
Yes,
why is some length? I don't know. Maybe you should give it a name. It's some length s.
Okay.
So there are s pairs there. You just arbitrarily for each one of these s coordinates put the xi part in the u and the xj part in the whatever order.
Yeah.
Xi
So
will appear many times in the u vector.
yeah, exactly.
This
So,
is like halfway, right? Because the u and v may not be consistent
yeah.
themselves and
Yeah, just a second. So that's a good point, but just a second. Before, just to repeat what Avi says, u and v are just going to be constructed from x by repeating some of the coordinates of x multiple times and permuting them. So eventually we have for each term at the same place in u and v, in one place we will have xi and in the other place xj. So eventually we would have y equals u times v with coordinate-wise multiplication. And as Gilad said, we still need, I mean, we don't know that u and v are consistent with x again. Maybe the prover again gave us something that has no connection whatsoever to x. But that's a linear test. So we can use the linear PCPP to verify it, right?
just to make sure, if the y is indexed, we have all these pairs, so y is indexed by those pairs.
Right,
So does x and y.
right. So does u and v.
U and v, I mean, yeah.
Yeah. So actually, it is not completely correct that we can. Okay, let's. Okay, first of all. So now what I would like to do is to check that y. So I can check that u and v are consistent with x using the linear PCPP, and then I can just choose a random coordinate of y. Choose a random coordinate of y and check that yi equals ui times vi. Am I done now? Right, so there are a few problems here. First of all, I can't really check that, use the linear PCP to check that U and V are consistent with X, because the linear PCP only checks linear claims up to some distance. So the prover could cheat me by giving me U and V that differ from X in one coordinate. But this can be dealt with if I ask the prover to also give me the error correcting encoding of all those things. And now, if the prover gives me the error correcting encoding of U and V, and those are going to be linear codes, then I can check that the prover gave me an code words that are consistent with X. And now, even if the prover is trying to cheat, even though the linear PCP only guarantees that something is close to be correct, since I'm talking about error correcting codes, it means if something is close to be correct, I can decode it to something that is correct. So this is not a problem. The other problem is that it could be that U and V do not really satisfy Y equals U times V. It could be that Y and U times V differ at only one point. And I can't use the linear PCPP to check that because, I mean, this is not a linear claim. And if they differ only in very few places, I will also have very small probability of catching them using this test. So here is where I use the multiplication codes.
But so it's the fact that you have the code word for U in one of the families of codes, the code word for V in one of the other families, and then that has to be contained in.
Right.
Okay.
So what I'm going to do now is to ask the prover to give me also CU and CV, where this is supposed to be equal to CA. Avi, when are you going to convince them to switch to whiteboards?
The chance is close to zero. You can read the song in my office, then I convince them of it.
Okay, so what I'm going to ask the prover to give me is the encoding of U using CA, the encoding of V via the code CB, where now I'm using the multiplication codes CA, CB, CM that have this multiplication property. And I'm also going to ask the verifier, the prover, to give me what you may call CU times V, which is supposed to be equal to CU times CV. And now notice few things. First of all, because I assume that these are systematic codes, CU contains U, CV contains V, and in particular, C of U times V is supposed to contain Y. And now these are all linear conditions that I can check using the linear verifier. I can check that CU is indeed the encoding of U. I can check that CV is indeed the encoding of V. I can check that CU times V contains Y. These are all linear conditions that I can check using my linear verifier. And again, the closeness is, the fact that I'm only verifying closeness to being correct is not a problem because I use error correcting codes. So the only thing that remains, the only condition that I can't verify using the linear condition.
How do you know that the code word that you get, so you have CU, you have CV, you have CUV.
Mm-hmm.
So if I give you a, purported code word in CUV, you can check that it's in the code. But how do you check that it's consistent with?
Exactly. Great. That was exactly the next thing I was going to say. Thanks. So there is one condition that I cannot check using the linear PCP, and that is, as Ankur said, I cannot check using the linear PCP that this equality is true, because this is a non-linear condition that CUV actually equals CU times CV. But what I can do is now to check for a random coordinate that CUV at I equals CU at I times CV at I. And now the point is the following. This is a code word of the code. This is the code word of the code CM. This is also a code word of the code CM. Or I can check using the linear PCPP that CUV is a code word of CM, because this is another linear condition. So now, if they are different code words, if this is not equal to this, they'll have to differ on a lot of coordinates, because this is the property of error correcting codes. Any two code words differ on delta fraction of these coordinates. So I have a probability of delta to catch them. Questions?
So do you assume that the code, so you said that you are going to check that CU is the right code word of U. So you assume something about the code, the circuit that generates the
Yes, I
code.
need the circuits to actually be small.
So that's another condition for the amplification.
Yes, but I can also do it using, say read Solomon codes have quasi-linear.
You can do that using polynomials.
Right, right. That's a good point, actually. Right.
So can you repeat?
Hmm?
Can you repeat discussion?
Uh,
Everything discussion.
Oh, my discussion with Ran?
Yes.
Oh, okay. That again goes back to the fact that to what I'm trying to hide, that I can't really talk only about the length of claims or the length of vectors. I need to talk about the size of the circuits that are used to represent the claims. And what Ran said, and is right, that in order to use the linear PCP to verify membership that says CU is the correct encoding of U, I need the code CA to have a small circuit that encodes a message or at least to have a small circuit that verifies that a string is a legal code word. And polynomials actually have such small circuits that verify that a code word is in the code. You can use a fast Fourier transform or something like that.
You want to do it exactly, you don't want to use the linearity check with I.
So, but for our purpose, again, this is a fact that I'm trying to hide. So let's keep with this strategy of denial.
Can't you use the linearity to code as a subspace, and you use the linearity test to check that U is in this linear space that is induced by this code?
Okay, what I want to use a linear PCPP to verify that CU belongs to the code. Linearity test would work only if CA was the Adamard code. Otherwise, I can use the linear PCPP to verify that CU belongs to the code. But the linear PCPP needs to take as input a circuit that recognizes code words of CA. And now the point that Ran made is that the circuit that recognizes CA has to be small, because this is how the linear PCPP works. Okay, great. Other questions? Okay, so this concludes the construction of the PCP from the linear PCP. Of course, I didn't give the full formal details. One needs to show that the main thing that I didn't show you, but is not very hard, is to show that it's not that bad that the linear PCP only verifies that things are close to be in the right subspace. And as I said, it's not too bad because we use error correcting codes, and whenever something is close to be correct, we can decode it into something that is correct. This is not a very hard proof, but it will take some time, and I don't want to spend it. So I guess that would be a good time to take a 10-minute break. Okay, great.
What's coming after the break?
The verification of square root n claims using square root n queries. So, so now we'll discuss the second step we mentioned. That is, we have square root n claims of size about square root n, and we wish to verify all of the small claims simultaneously using square root n queries. I'll say more exactly what I mean. Maybe I do better. No, okay, I'll use this board. So now the verifier has, okay, let's say that k equals O tilde of square root n is the number of smaller claims, and m O tilde of square root n is the size of the smaller claims. So now the verifier takes as input subspaces W1 to WK and gets Oracle access to vectors. Oh, these are of 0, 1 to the m. And it gets Oracle access to x1 to xk and to a proof pi. And the verifier want to make O tilde of square root n queries and it makes about square root n queries to all these vectors and pi, and it wants to verify that all the claims are satisfied. Belongs to Wi. Now, the completeness requirement is as usual. If all the claims are correct, if for every I, xi belongs to Wi, then there exists some proof that will convince the verifier to accept with probability 1. The soundness, one should be a bit more careful. So we need to explain what we mean by saying that we verify all of them simultaneously. So what we mean is that if there exists one I such that xi is epsilon far from Wi, that is, if even one claim is far from being correct, then we want to reject with probability, and here it will be epsilon over polylog n. Because as we said, a rejection ratio, rejection probability of 1 over polylog n is sufficient for our purposes. So this is what we want to do. And note that in particular, we cannot just solve this task by choosing a random claim and verifying that this claim holds. Because if there is only one claim that is false, we won't catch it with good probability. So the way I will describe the construction is to start from a very simple case and gradually go to the most general case. So let's start with the simplest case. Where all the subspaces are the same. Say they are all equal to some subspace W. Something very similar to that. So what we will do now is the following. We will ask the prover to provide us, well, not asking the prover. The verifier is given oracle access to the vectors x1 to xk, so let's arrange them in a matrix. Call this matrix M. So this matrix M is just all the vectors, x1, x2, they are the rows of this matrix, xk. And what we will ask the prover to give us is a second matrix, M prime, that is constructed by encoding each column of M prime of M using some linear error correcting code. Okay. This is encoding via some error correcting code, call it C. And say that C has a linear length and a constant relative distance.
And it has in the whole matrix.
It has?
Row-wise.
No, column-wise.
Column-wise.
So we encode columns. And what the verifier will do now is one of the following. Or it will actually can do both things. It will choose a random row of this matrix and check that it belongs to W. This should be satisfied because every row of M prime is a linear combination of a row of M, and therefore if all the rows of M belong to W, all the rows of M prime should belong to W. Then the verifier will choose a random column of M prime and verify that it is the right encoding of the corresponding column of M. So clearly, we are using only square root n queries, or about square root n queries. So let's see, and it's clear why it should be complete. I mean, if M is the correct, if x1 to xk do satisfy the condition, the verifier will accept probability 1. So it remains to show the soundness. So, okay, so let's see how do we establish the soundness. So suppose xi is epsilon far from W. And let G be the set.
So, I mean, so what you're looking for is that many of, I mean, a constant fraction of the rows in this new encoding should be far from the subspace, right?
So,
And that's partially because that vector has to participate in the constant fraction, right? The corresponding vector.
that's the intuition, but I'm not sure that this is the formal, correct formal way to say it. So I'll give an intuition in a second. It will just be, I just want to make a few definitions that will make it easier. Okay, so so I want to define G to be the set of good columns. By good, I mean that good columns of M prime, that is that they are the correct legal encoding of the corresponding column of M. So now, if there are many bad columns, that is if G is smaller than 1 minus epsilon times M, we are done. The verifier will just pick a random column, and with probability epsilon, it will find a column outside G, and will reject. So we will reject with probability epsilon.
But so, I mean, in the case where all the columns are good, this is then, I mean, it's immediate, right?
It's all right. So this is the next thing I want to say. Just
and then, I mean, at least the intuition is that if there aren't, you know, I mean, so the bad columns can't affect its
Exactly. So now let me elaborate it, but you are right, exactly. So what we want to do now is to say, okay, so we have only very few, so we can assume that there are less than epsilon fraction of bad columns, so we will throw them away. So we now look only on M and M prime without
Maybe epsilon
we,
square 2.
no, yeah, it doesn't really matter, but yes.
Because you may have erased all the.
I just want what. Okay, it's a matter of less or equal, but what I want to say is that for eventually what I want to say is that xi projected to the coordinates in G is not in W, sorry, not without the square brackets. Projected to G is not in W restricted to G. Because Wi does not belong, because xi is epsilon far from W. So if I throw away less than epsilon of the coordinates, I can't be in the projected subspace. And now I'll explain the intuition that Ankur was saying. What I'm going to argue now is this. If xi is not in W projected to G, it means that it must violate some linear constraint of W projected to G. But then I want to argue that due to the encoding properties of the linear code, or due to the relative distance, it means that if xi is not in W projected to G, then many of the rows of M prime must violate this linear constraint that xi violates. So a bit more formally, there exists some W perp of dual space of W projected to G such that such that xi violates this linear constraint. That is, if I take xi, okay, I should say here one more thing. I assume that xi is a row of M prime because the code is systematic. So what this means, so now let's look at what happens if I multiply M prime by W perp. Sorry, not M prime projected to G. So in M prime projected to G, all the columns are code words of the code. So this product is a linear combination of columns of M projected to G. So this product is also a code word of the code C. However, the ith coordinate of this code word is non-zero. So M prime restricted to G times W perp is non-zero code word. But if it is a non-zero code word, in particular, it means that it is delta far. There is a relative distance of delta between this code word and the zero code word. So it has many non-zero coordinates. But this means that many rows of M prime G violate the linear constraint W perp.
That doesn't mean that it's far from W.
Right, but I don't need it to be far from W. I just need them not to be in W, because now the verifier is going to choose a random row and verify that it belongs to W.
Yeah, but the soundness condition for testing this linear test requires that either it's, you just tested it under the condition that it's far away. Now it will not be far away, maybe fair from.
But this is the condition that I have. But I have that xi is epsilon far.
But you're not testing it.
But now what I got is that now many rows of M prime do not belong to W. They can be very close to W, but
So
the
you are looking at all of the rows.
right, exactly. The verifier now chooses a random row of M prime and reads it wholly.
Yeah.
Okay. So and this so this is all the soundness analysis. Questions?
Just to repeat the test, you first check, test the column and then read the random column and then read the random row.
Exactly. Okay, so this is the simple case. Now we'll move to a more interesting case. So this is the case I call colorable constraint systems. So let's look at the subspaces W1 to WK. And I want to say that each of them is characterized by a set. Okay, maybe I'll move to here. I want to say that each of the subspaces W1 to WK is characterized by a set of linear constraints, where linear constraints are just vectors in the dual space. So let's say that Wi is characterized by Si, so this I is here. And Si is just the basis of Wi perp of the dual space. And yeah, this is just a parity. If you like, Si is just a parity check matrix for the subspace Wi. Now I'd like to say, and now I want to look on the set S equals S, which is the union of all the sets Si, and I'll say that S is chi colorable if we can color it using chi colors such that no two constraints of the same color, or actually for every two constraints of the same color, have disjoint supports. So I want to color all the constraints of all the vector spaces together such that using few colors, such that if two constraints have the same color, they don't touch the same coordinates. Those two linear constraints of the same color do not involve, do not share a coordinate that they involve. Sorry?
The SIs are bases
For the dual spaces.
Right, and you're coloring the bases rather than the whole vector space.
Rather than the whole dual spaces. Yes, right. And the point is that the only question is whether I can choose some SIs that have this property. Now, and
Or you really want them to be sparse?
yeah, of course, as usual. But yes, so later I will claim that the general case can be reduced to this case. And now, also I'm now going to show how to solve this case by reducing it to chi instances of the simplest case.
So we only to imagine it, so suppose we have S as a matrix, so you put everything to huge matrix now, and you want to color two rows of the matrix in the same color, if you have like things 0 here and things that 0 here and not 0 here.
Yes, if you arrange all the constraints in S in a matrix, you want to color the rows such that every column sees only one color. So every column sees each color at most once.
The non-zero coordinates, yes.
Yes, something like that.
So you want the chi to be some power of n, also small power of n.
What's a small power of n?
Chi.
I want it to be about polylog n, but I can actually.
You can play with the parameters before having.
Yeah, but the point is that I can actually make it 6.
You
So
can make it 6
for the general case.
so you have
The general case,
subspaces.
yes.
So you have about n matrix of size n by root n.
Right. I have square root n subspaces of size, over square root n coordinates, and I can reduce them to other subspaces of size over square root n times polylog n coordinates that can be colored using cis colors.
I mean,
It's
is
not.
that through the probabilistic method, or?
No, it's going to be very straightforward. Actually, since I'm not sure I will have the time to show it, I can say a few words about it now. What I'm doing essentially is that you can, by adding a few to each subspace auxiliary coordinates that will serve as an auxiliary proof, you can embed the constraints of each subspace on a routing network. And you can choose a routing network that is, say, edge colorable, and then use the coloring of the edges. We're embedding all the subspaces on the same routing network, and then we'll use an edge coloring of the routing network to color all the constraints. This is in 2 sentences. Hopefully, I will have time to say a bit more about it. Okay, so now let's see how to do this colorable constraint system case.
So wait, you're using this routing network to construct a matching of some sort?
To construct what?
A matching or what?
Okay, this either I'll manage to show it today, or
Ask you offline.
yeah, hopefully I will show it today, but otherwise we'll discuss it offline. Okay, so so what I want to do now is to reduce this colorable constraint system case to 3 instances of the simplest case, where all the subspaces are the same. So I'm now going to show how. So now I'm going to show how do I construct each of the instances of the simplest case. So now, for each color, actually, we are going to have an instance for each color. So let's fix a color C. Oh, I don't know, is C a good letter? C. Okay. Let UC be the space characterized by constraints of color C. So UC is just the subspace characterized by all constraints of color C, no matter from which WI I took these constraints. Take the constraints of color C from all the subspaces WI, and I use them to define UC. And UC is going to play the role of W in the instance of the simplest case I'm constructing. And now, for each xi, I'm going to construct a new vector. Construct a new vector xic defined as follows. Xic at coordinate j equals just xi at j if Si has constraint of color C that touches J. Okay. And 0 otherwise. So I just go over xi, and whenever I see a coordinate that is not touched by any constraint of color C in Si, where Si again is the set of constraints that characterizes Wi, I'm going to zero this coordinate. And now I claim that all the claims hold, that is for all xi, for all I, xi belongs to Wi, or you know what, forget it. Particularly xi belongs to Wi if and only if for all C xic belongs to UC. I will get to that. What I'm going to do now, so why is this equivalence correct? The point is that, okay, if xi belongs to Wi, it means that xi satisfies all the linear constraints of Si. So this means that for a particular C, in particular, xi satisfies all the constraints of color C. But I didn't touch, but in constructing xic, I didn't touch any of the coordinates that are touched by constraints of color C. So they remain the same, and xic still satisfies these constraints. And on the other hand, if you look at the constraints of color C that do not belong to Si, I would like to say that xic also satisfies these constraints, because these constraints of color C that do not belong to Si touch only coordinates that I have zeroed. They cannot touch those coordinates that I did not zero, because the only coordinates that were not zeroed are those that are touched by some constraints of color C that are in Si. So by the property of the coloring, these coordinates cannot be touched by constraints outside Si that are of the same color. Right. The linear constraints involves the coordinate J. It is in the support of the vector, yes. Exactly. On the other hand, if for every C, xic belongs to UC, it means that for every color C, xic satisfies the constraints in Si of color C, just because it belongs to UC. And I would like to say that this means that xi also satisfies all the constraints of color C in Si, because these constraints only involve the coordinates that were not zeroed in xic. So xi also satisfies these constraints. And therefore, xi satisfies all the constraints of all the colors, and it belongs to Wi. So now it just suffices to check this claim. Just a second. what we are going to do now is to ask the prover to give us all the vectors xic, and we can verify this claim using the linear verifier for each color. Sorry, not using the linear verifier, using the simplest case as before. We have a simplest case that checks for a lot of vectors that they all belong to one subspace. And this is just this sort of claim, so we will just verify it using this way. Yes, Ilya?
Trying to imagine pictorially what it means. It's like you take the whole space, like introduce a new dimension, like time or something, and then you cut the whole thing and cross the dimensions into chunks, and then you check like this, each chunk separately. Something like this happens here?
You may think of it like this, I guess. I'm not sure.
I'm trying to get the more, not the formal, the more intuitive thing behind this.
I'm not sure that geometric intuition is the right intuition. I mean,
I'm sure you have a better intuition.
the basic idea is that I want to reduce the colorable case to instances of the simplest case. So what it means is that I want to allow myself to transform for each vector, to construct for each vector xi some vector xic that will allow me to check that xi satisfies the constraint of color c that xi needs to satisfy, but I also want that the constraints of color c of other subspaces will not interfere in this check. So the coloring condition guarantees that constraints of the same color that belongs to other subspaces do not interfere with what I want to check. And the way that I guarantee that they don't interfere is just by zeroing the coordinates that do not involve. Okay, maybe I just don't see it. Okay. So, okay, I think I'll skip the formal construction of the verifier. So in general, what I'm going to do now is I'm going to ask the prover to give me all the vectors xic and use the verifier of the simplest case to verify that all those instances are correct. But still, I am left with the problem of verifying that the vectors xic that the prover gave me are consistent with the original vectors xi. I mean, it could be that the prover gave me just arbitrary vectors xic. I want to verify that the prover did not cheat me at this point.
Is it true that the subspace Wi is just the intersection of the subspaces U?
No, it's not. It's just, it's not true because I didn't write here xi, it's xic. I mean, in order to construct xic, you need to zero out some of the coordinates. Okay, so the only problem I have now is to check that xic are consistent with xi. And the point is essentially that this is just verifying that xic was constructed from xi by zeroing some of the coordinates. And this can be checked by writing xic equals xi times some other vector zic, where zi is just 1 where I don't want to zero, and 0 when I do want to zero. And the point is that these two can be checked using the multiplication codes. So this is some kind of multiplication condition. And now, for each vector xi, I can use the multiplication vector codes to verify this claim using a constant number of queries. And I have square root n queries, so I can afford to do it for each of the xi's. So I can verify the consistency. This is very broadly or very roughly what I'm doing.
Is it really enough to be able to do that for some arbitrary ZIC?
Hmm?
Don't you have to check that this particular ZIC has some structure that's like negative from?
No, because the verifier actually knows ZIC. Um, the, ver the vector ZIC is just derived from the coloring and from the subspaces WIs. So the verifier can just construct the ZICs himself. He doesn't need to rely on the prover to provide him with the vectors ZIC.
Oh, I see. So the multiplication code is even playing a role in the linear PCP.
Right. That's actually an annoying thing that I would be glad to get rid of, but I don't know how to do it. So yes, the multiplication code is also playing a part in the linear PCP, in the construction of the linear PCP, and I would really like to get rid of that. Hmm?
Don't skip from the algebra.
Okay. Okay, so now I would like to say, in the time that I have left, I want to say a few words about the general case. So I want to reduce the general case. No escape from the chucks, I guess. Okay, so now I want to reduce the general case to the colorable case. So I have W1 to WK and X1 to XK. And what I'm going to do now is to construct the very corresponding spaces W1 prime to WK prime and vectors X1 prime, XK prime, such that the verification of the claims about the WIs and the XIs are going to be equivalent in some sense to the verification of the WI primes and the XI primes. I'm not going to say what this equivalence is formally, but it's just like, when you reduce a circuit sat to 3 sat, the formula you end up with is in some sense equivalent to the original circuit. And I'm going to construct, and the point is that the WI primes are going to satisfy the coloring property. And as I mentioned, the way I'm going to do it is by using what's called routing networks. So, what can I erase? I can erase the multiplication codes. So a routing network G is a graph VE with some special set of vertices Z contained in V, such that for every permutation sigma on Z, I can find a vertex disjoint paths that connect each V in Z to sigma of Z. And of course, there are vertices joined up to their first and last vertex, but it doesn't really matter. And these are routing networks are just come from distributed computing. What it means is that if the vertices in Z represent computers that want to send messages to each other, then I can route the messages in a way that every computer in the whole network only need to process one message. And now, in order to use them here, okay, so let's say that the W1 to WK are characterized by the constraints S1 to Sk, and I want to construct new constraints, S1 prime, new sets of constraints, Sk prime. Oh, and I need to say all of those vectors and all of those vector spaces are in 0, 1 to m prime for m prime equals m times polylog m. Okay, so now what am I, and this polylog m comes from the fact that we have routing networks in which the total number of vertices is just z, the size of z times polylog z, and are 4 edge colorable. Okay, so now I want to focus on the case in which all the original constraints I want to verify in S1 to Sk are disjoint equality constraints. Let's focus, say, on S1. Then S1 just consists of equality constraints, xi equals to xj, and all the constraints in S1 are disjoint. That is, if I have xi equals xj, I can also have xi equals xk. And it may seem like a trivial case, but actually, in a sense, this is the hardest case, because intuitively, if I can deal with equalities, it means that I can move coordinates around, and once I can move coordinates around, it makes the coloring very easy. So it's, in a sense, it suffices to deal with equalities. I don't want to go into the details of why it suffices to deal with disjoint equalities. It's not very interesting. So now the
Again, you need to use the fact that the description of W1 to WK is small. Right?
Of course, yes.
So this claim is again not exact for any W1 to WK.
Of course, it's always with small circuits. So now the point is this: I'm going given S1 and the equalities here, I'm going to identify the okay. Now the vectors I'm constructing are over m prime coordinates, and I look on the first coordinates of m in M. They will still contain the original vectors, x1 to xk. And I'm going to identify the coordinates. Okay, now I'm going to, in the graph G prime, I'm going to identify all the coordinates m prime with all the vertices in V. And I'm going to identify the original coordinates m with the vertices z. So, and now I have a bunch of equality constraints that I want to check. So I will construct a permutation sigma such that for every equality constraint of the form xi equals xj, the permutation sigma will map the vertex I to the vertex j. And I will find a set of vertex disjoint paths on the network that route this permutation, that connects hxi to xj. And then in, say, Si prime, or in, say, S1 prime, if I'm discussing S1, I'm going to have an equality constraint for each edge in these vertex disjoint paths, for each edge that participates in these vertex disjoint paths. So I'm going to say it again slower and hopefully clearer. Okay, let's focus on S1. I want to construct a subspace W1 prime that is somehow equivalent to W1, and the vector X1 prime that is somehow equivalent to X1, and a set of constraints, S1 prime, in a way that such that after the construction of all the subspaces, I will be able to color them. So let's focus on the construction of S1 prime. What I'm doing here is now to construct W1 prime by extending W1, by adding more coordinates, such that the original coordinates of W1 will be identified with the set Z of vertices of the routing network, and the rest of the new auxiliary coordinates will be identified with the rest of the vertices. Now, now the equality constraints give me pairs of. I can think of them of pairs of vertices of Z, because Z is identified with the original coordinates, and each equality constraints look like xi equals xj. So now I want to find a collection of vertex disjoint paths in the routing network, such that for each equality of the constraint in S1 of the form xi equals xj, I have a path that connects xy to xj. And now in S1 prime, I'm going to put an equality constraint for every edge that participates in those vertex disjoint paths. Okay, so now if some vector x1 prime satisfies all the equality constraints in S1 prime, then eventually it will also satisfy all the equality constraints in S1. Just because if xi is connected to xj by a path, and there is equality constraint on each edge in this path, eventually xi must be equals to xj. And I will do this construction for all the sk's, and we'll construct S1 prime to sk prime. And now note that if we look in all the constraints that are, if I will look at the set of constraints S prime equals the union of Si prime, then all the constraints in S prime corresponds to edges of the routing network. Every constraint in S prime is an equality constraint that corresponds to some edge of the routing network. But this means that if I take a 4-edge coloring of the routing network, I can use it to color also the constraints in S prime. And this coloring will have the property that I want, that no two distinct constraints touch the same coordinates, just by what edge coloring is. So this gives me a way to transform the original problem into a problem that can be colored using 4 colors, but this is only if I have disjoint equalities. But I can move to the general case using 2 additional colors. And that's about it.
How do you move to the... you assume that the dual is sparse without loss of generality again, like
yeah, again.
You can break
yeah, so
check,
for
parity check of like
exactly.
Yeah, but
And
if you are allowed to do this, then I don't know why you need the permutation network.
Why?
I mean, suppose that instead of breaking it to root n by root n,
Mm-hmm.
you just did it n to the third problems each of size n to the 2/3,
Okay.
but with sparse constraints,
Okay.
right? So just put them under each other. So you have now a matrix of n by n to the 2/3,
Mm-hmm.
and every column has about n to the 3rd ones in it.
Okay, but why would they be colorable?
Just by sparsity, I mean the same, but by degree. The degree in this graph is n to the 3rd. No, they will not be constant colorable. They will be colorable by n to the 3rd color. That's the density of the matrix.
Okay, let's take it offline.
So I'm just, okay, yeah, we can take it offline. Then I
because
just think that
no,
you will have just n to the 2/3 problem of size n to the 2/3 and you will get the same result.
oh, maybe I can. I don't know. Maybe you are right. Maybe I can have. But then I will not. But then the recursion would give me a very.
Still be a log line.
No. So now, if you like look at the blow up, I would get by when doing the composition, I would get a PCP of polynomial length. I don't know. Maybe it will still be interesting. Maybe it will be a PCP of length n to the 8. But okay. Any questions? Yes.
So suppose you allowed yourself some algebra, it's still not clear. I mean, is it clear how you would do a linear PCPP any easier?
Sorry.
Suppose you allowed algebra,
Mm-hmm.
then
Oh, I see. Not that I know.